Okay, welcome everybody. I'm Gary Bergcross, co-organizer of the Ontology Summit for 2023, along with James Overton. It's April 19th, 2023, and we have our final individual session on topics relating to making ontologies and related semantic resources easier. So with that, let me introduce our speaker today. Our speaker is Martin Skjæveland, who has a bachelor's in natural science from the University of Bergen and a master's in informatics, as well as having been a postdoctoral researcher. Postdoctoral researcher at the Department of Informatics at the University of Oslo, where he's now a researcher. He is also an adjunct associate professor at the University of Skjæveland. Martin lists his research interests as knowledge representation, ontology engineering, and in particular, tools and methodologies for developing large-scale ontologies and the use of ontology-based systems in industrial settings. So I think this is a nice complement to some of the sessions we've had in the biomedical field and the earth sciences and so forth. He was previously a consultant with Norsk Vitters, now DNV-GL, working with information management, ontologies, and semantic technologies. Martin is the developer and lead of the OTTR or OTTR framework, all of which makes him well qualified to talk to us today about pattern-based ontology development with those reasonable ontology templates. So please welcome please welcome Martin.
Yeah, it's almost the same in this respect. So thanks for that. Let me share my screen. Let me just rearrange some windows here. Do you see my screen?
Yes.
Yes, we can see it.
Reasonable ontology.
So I think Gary already did my first slide. So I'll just continue. I'll start with giving some insights into the use cases that motivate the invention of the OTTR project. And the most prominent one that I've worked with is one which I call the Able use case. So Able is a construction company that makes large oil and gas platforms, primarily the ones you see in the background. And they have created an ontology which is very large. It contains over 100,000 classes. And these classes, they represent, or the ontology as a whole, represents different industry standards, and also what I here call creative designs. And a creative design is a combination of different standards. So it would be, for instance, a standard for the dimensions of pipes and the coating of the pipe and the material of the pipe. And these are creative combinations that the engineers at Able do. What they use the ontology for is to automate highly complex but trivial work. What I mean by that is to check that these combinations of different industry standards are compatible. So I mentioned a few different standards, but there are more, and they also need to ensure that their engineering design is according to different regulations, both international and national. And this is, in a sense, trivial, but also highly complex, and that's why they need to hire engineers. But engineers are very expensive, so if they can do away with some of that work using ontology reasoning, that would be good. And that's, of course, what they have been able to do with these ontologies. So they can do then verification of these requirements using ontology reasoning. And this has led to reduced cost and improved quality and accountability. I will continue by showing some slides that Able themselves have produced. And they have come up with some requirements for building large industrial ontologies. So these ontologies, they need to, of course, support a large number of classes. And they have usually very similar shape. I will show an example on the next slide. they need to support a large number of different industry standards, which define often very similar things in nearly the same way. And to ensure, since the ontology becomes very large, it's important that the modeling is consistent. And by that, I don't mean semantically consistent, but also that similar things are modeled in the same way. That's important to ensure consistent use and also the maintainability of the ontology. Since the ontology needs to cover many different domains, it has to be built in a collaborative manner because different subject matter experts need to be involved in the work. And of course, since it's large, you need to support automated mechanisms for handling the quality of the ontology. So this is a typical type of data that is recorded in the ontology. Here we have some flanges, and they come from different, or in this case, the same standard. They have different sizes and support different pressure classes. So this slide is about the tools to create an ontology, and we have Protégé, but Protégé is not suited for the task, and that's because the sheer size of the data, and that, of course, humans are not good at these repetitive tasks, and Protégé is not suitable, at least in the common sense, for collaborative ontology development. Also, the tool is not suitable for giving to engineers which are not familiar with semantic technologies. The favorite tool of engineers is Excel. Of course, Excel is not a good database management tool or a data management tool. So since you can put anything in there and there's no schema compliance and so on. The research proposition for the Reasonable Ontology Templates project is the following. We want to improve the efficiency and quality of ontology engineering for large-scale ontologies, just as I presented. The problem with the current ontology engineering tools and methods is that they are too low level, and this makes ontology construction repetitive and error-prone. That again makes it difficult to engage end users and difficult to generate sustainable large ontologies and to maintain them. So what we want to propose is the need for abstractions in ontology engineering. We want to capture and instantiate recurring modeling patterns, and we want to develop different formats and tools which are adapted to the different roles that come into play in ontology development. So the reason for abstractions is very simple and very naively presented on this slide. The idea is that when you increase the abstraction level, you also lower the competence necessary to work with something. And by lowering the competence, you increase the number of possible users that can use this. Let me illustrate that with an example. On the left, we have some assembly code that writes hello world to screen. At least that's what I found Googling. And on the right, we have the same thing in Python. What we can immediately see is that the Python code hides a lot of complexity. Here, I assume that the assembly code talks about memory locations and moving things about there. This I really don't care about usually when I want just to write hello world to screen. So there is a separation of concerns. If I was interested in the memory locations and such, then perhaps assembly code is the right language for me. If I'm not, then Python seems a better choice. So Python and assembly code supports different type of users. The situation in ontology engineering is the following. We have RDF OWL, for which we can express ontologies, but we have no established candidate for an abstraction language. There is something slightly better, which is Manchester OWL, but we still need to do low-level OWL coding in order to create ontologies. And it's impossible not to care about logic when creating ontologies. And that's because there is no proper abstraction mechanism. And this is where reasonable ontology templates come into play. So OTTR is a macro or / pattern language for creating or interacting with knowledge bases. With OTTR, you can define abstractions over RDF and OWL. So OWL by way of RDF, really. And you can use OTTR to represent and instantiate modeling patterns. By using OTTR, you gain well-known benefits known from other fields such as software engineering for abstractions, such as creating, which makes it helpful for creating, maintaining, and communicating ontologies and knowledge bases. All our stuff is available at the OTTR XYZ website, and we do have an, it's not terribly large, but large enough active community of industrial users. Let me illustrate what OTTR is by an example. On the left here, we have a pattern that repeats itself. The blue stuff varies in the pattern, but the black stuff stays the same. And I can single out the pattern and replace the blue stuff with variables, which I give names. So I name one variable with name and one with label. I can now give this pattern a name. I call it pizza. And I list the variables that occur in the pattern. OTTR uses a recursive data structure, so there is also a pattern for representing RDF triples. What we now see is a complete OTTR template. I can now instantiate this template by referring to the name of the template and provide arguments that match the parameters of the template. So the three instances that I have here, they accurately represent the same RDF that I see on the left. I said that OTTR is a recursive data structure or uses a recursive data structure. So I can also define a template that represents the subclass of modeling pattern, even though it's simple. And I see that I make use of this pattern here. So then instead of using the triple pattern, I can use my subclass of template. What have we gained? We have now abstractions. So we have a formalism or a concept, which has a name here exemplified by pizza, which is an abstraction over a simple modeling pattern. By using abstractions like this, we follow the dry principle. So instead of repeating this tedious pattern 3 times, I have a more simple way of doing that using just instantiations of the pattern. My patterns are compositional. So the pizza template relies on the basic triple template and the subclass of template. So for illustrative purposes, assume that the subclass of template or the pattern for representing subclass relationship in OWL is much more complex than this. Then a user of the subclass of template only needs to know that to use it, you need to provide 2 arguments. And the complexity of the pattern is hidden inside the subclass of template. We get uniform modeling. So every time we make use of or instantiate the pattern, we get the same result. And we can separate the design, which is represented by the templates, and the content, which is represented by the instantiation of or the instances of the templates. So different people can design the templates than those that instantiate the templates. This mechanism is also a way of ensuring completeness of input. And what I mean by that is I cannot create a pizza without providing all the arguments, in this case, to the template. So I cannot create a pizza without a label in this case. Also, this input format is very simple. So it is a tabular input format, which lends itself not only to the format what we see here, but also we can get data from tabular sources like spreadsheets and relational databases. And the mechanism from going to the right-hand side to the left-hand side, which is RDF, is very simple. It's based on just ordinary substitution and macro expansion. And I can illustrate that by an example. So the instance here is expanded to RDF by replacing the variables with the arguments. And I do that recursively. So here I have a instance which is not an instance of this basic triple instance, so I need also to expand that one, and I do that and end up with triples that represent the pattern here. That's it. We have some additional features in OTTR, and we can give our parameters types. So now I just go back. So in this example, my parameters didn't have any type, but we can give them types. So we can say that the first parameter needs to be an OWL class, and the second one needs to be an XSD string. I will demonstrate how this works on the next slide. We can also have types which are lists. So I'm now changing the signature of the template and saying that instead of just taking a single string, I can take a list of strings, and I can do operations on that input. So I can for each element in the list, I can send that to one template. So it's kind of a loop operator over the instances of the list. I can specify parameters to be optional. So here I say that the label is optional by adding this question mark, which means that I can instantiate this template without providing an argument for the second argument, the label argument. I can also specify default values. So if I do not instantiate or give an argument to the second one, it defaults to the string Grandiosa, which is a very popular Norwegian frozen pizza. I can also specify my parameters to be non-blank. That means that a blank node is not a permissible argument to the parameter. Let me demonstrate how type checking works. I have my subclass of template, which has the parameter OWL class for the first and the second argument. Now I instantiate it twice, here giving a URI and here giving a URI, while for the second one I give a string. And you can think about which one is correct and which is not. So the first one is okay, because URIs can be OWL classes, while the second one is not okay because a string can never be an OUL class. We can also type check template definitions. So assuming I have here a pizza template, which contains a body of 3 templates. Now the question is, there is an error here, but where is it? And then type checking becomes very helpful. So this one is not okay because here I'm sending a variable which has a string as type to this first argument, which needs to be an OUL class. And strings and OUL classes are not compatible types. So this will be flagged as an error. We can also do, type check consistent use of parameters, arguments. So let us assume that I start with this template. So I have a template that takes just 1 argument and it sends it to my pizza template, gives a blank and giving a blank node. And a blank node is a permissible value for an OUL class parameter. Now assume, no, sorry, I said something wrong. The blank node is sent to a parameter which is typed as a string. So I pointed to the wrong template, sorry for that. So, but again, that is not a problem. A string can be represented by a blank node, or a blank node can represent a string. But now the error occurs when I add a new instance to my template pattern and send the same blank node to a parameter which is typed as OUL class. Now my blank node is given 2 types, XSD string and OUL class. And OUL class and XSD string are not compatible. So this would be also flagged as an error. Some of you may wonder, how do I know that my pizza is a class? And the question is, the answer is that we don't. But the similar as this is, we can check this with consistent use. So my URI pizza would then be given the type OUL class. If I now use the same URI for something which is not compatible with OUL class, so that could be, for instance, OUL object property, then that would also be given as an error. So I think I will now just demonstrate how it can look like. So this is the homepage of OTTR XYZ. And from here you can navigate to a primer. And the first one is the fundamentals. And the fundamentals explains all the fundamentals. And if I scroll down to a blue box, the blue box is an interactive demo. So here I have 2 instances and I have a template. I can now run the expansion. What it does is it translates the instances into RDF. Now, just to test that type checking works, in this case, maybe I should zoom in a bit. My person template has parameters which have which are not typed. That means that they're given the most general type, which is RDFS resource. Now I can give, for instance, the second one. I can say that the second one needs to be an IRI. If I now run that, I will get an error saying that my string, which is strong, has a type XSD string, which is not compatible with OTTR IRI. So OTTR IRI is the type that we had to invent in order to represent IRIs. if I now say owl class, I should get a similar message, because owl class is a more specific type than otter IRI. Okay, let's continue. What I will now show is a more complex example of a template. And the template is taken from, or the pattern the template represents is taken from the well-known pizza ontology. The pizza ontology contains 22 different pizzas, and they are all subclasses of the class name pizza. The pattern looks like this. A margarita is a named pizza. It has a country of origin. It has multiple toppings, and it must have these toppings. This pattern can be represented by the following template. We have the template name, and we have our arguments. We take the IRI of the pizza, in this case margarita. We have an optional country of origin, and we take the list of toppings. What is interesting in this example is that this is a demonstration of what we can do with a list argument. So in this case, we send the list into a template which creates a union of class. So this blank node here is a class which represents the union of all the toppings. So this would be the parentheses that we see here. And the sub-object all values from is this axiom that says that margarita is the subclass of the universal restriction to this class, which is the class of the union. Now, since I, for each of the elements of the list, want to make an existential restriction, I can do that by applying an operator to this instance, which I call cross, and also mark, because it could be that the template takes multiple list arguments, so I have to mark which ones should be, for which ones the operation should be applied. So this means that for each instance of, for each element of the list, I create an instance of this template. So this means that, so let us show so this would be my instance. So for each element of the list, I create then an instance of the sub-object some values from template. Now, if I create my famous Norwegian frozen pizza and give it 4 arguments to 4 elements in the list, I get this expansion. Also note here that I'm using a special value for a missing, for the no value. In this case, we saw that Italy shows up as the country of origin, but we're too modest to say that Grandiosa comes from Norway, so we say none, which makes it not appear in the expansion. The tool that does the expansion, so which I demonstrated here, it is a Java application, and we have created a web wrapper for it. So this piece of code here is sent to a servlet that runs that code. An extension to that software can also read spreadsheets. So let me show the spreadsheet in full. So I can tag my spreadsheet with special commands, and the software will then read my spreadsheet and pick out that here is the start of instances that are instances of my named pizza template, which is the one that we saw on the slide. And I say which columns give input to the different parameters. So I could change the order here or skip some columns if I wanted. Here are my list of toppings given to the Venetian pizza. I can now expand all of these instances and would get a whole lot of triples. I can quickly demonstrate that. So I can go to this in WebLutra. You can simply give your instances and play around. So this is the expansion of the name pizza. I can select my spreadsheet and say that the input is tab otter. I think I need to clear this. Now I can expand and I get all the pizzas as RDF. There is also an extension, or what to call it, that with which you can define mappings over relational databases or any database really, but we support Sparkle and SQL databases, where you can map queries over the database into tables that are expanded with templates. So an example of that we find also in the primer. So here is a very simple expansion. So this just sends a Sparkle query to DBpedia and instantiates, creates instances of the triple template. If I now run this, I will get just five triples from DBpedia. So an important part of the OTTR framework are the templates. And the templates that we saw in the more complex example, so the subclass of and so on, these are templates that represent OWL axioms. And we can put them together and define new templates, such as the name pizza template. We have published the templates that represents the OWL axioms in a library, and the library is located at TPL OTTR XYZ. So here you will find all the templates that represents the axioms in OWL. So these are the axioms that have a specific RDF representation. So one would be, for instance, equiv all values from. We've also published our pizza templates, so I can scroll to that. So this page here is generated from the template representation, the one that we saw on the slide. There is also a way of adding metadata to the template. So I can say that it has a specific status, it's of a specific version, and I can point to the previous version of the template. I list the parameters. So this one takes 3 parameters. I see the Stotter, which is our own format for representing templates, which is built on an extension of Turtle. Then we demonstrate how an instance is expanded. So we have a generated instance here, and we create a graph of that and display it. So this is the pattern that it expands to. And I can see the expanded RDF graph. There is also an interactive expansion here. So here we see the stepwise expansion. So for instance, the subclass of template expands to a simple triple, but sub-object all values from has a more steps involved. The dependency graph of the templates is also displayed. So the pizza template relies on these templates, which again rely on these and so on. And OTTR is the template that all depend on at the end. We see the list of dependencies of templates, and also we see the URIs used by the templates. These, I said that there is a stutter serialization, which is our own homemade one, but there is also defined a RDF vocabulary, which we call butter, for which you can specify templates and their instantiations. So the purpose of template libraries is to provide share reusable and stable templates for others to use. As we just saw, our own template library contains about 200 templates. These are mostly for OWL axioms, but also there are some modeling patterns for RDFS and RDF and some example ones. So we saw the pizza templates, but also some project ones that we have published as use case papers. We've also written up some library management procedures. So we think we should use, or we use semantic versioning of the templates, and use the templates are stored in a Git repository, and we use a publishing procedure which is similar to software publishing. We have also developed tools for checking the quality of a template library. These tools, they check if we have a complete overlap of some templates. So maybe you have defined the template twice. We also see if there is an overlap, if there are templates that use the same instances. This indicates that the template library could be refactored. These are similar ideas for quality checking of software code. Since templates rely on each other, this lends itself to a top-down modeling approach. So you could start, if you know you want to model the domain of pizzas, you could start by simply defining the input format that your template should take. So you define the signature and list all the arguments that the template should take. Then you can iteratively dig down and and select templates from the template library that represent logical axioms. So in this case, we have called the different layers that you would typically end up with system, domain, logical, utility, and base. System templates, that would represent the templates that are first instantiated. So that would be the templates that lie closest to the system that stores the data. Then you would have more abstract templates that represents concepts in the domain. So name pizza would be such a concept. Those templates again would rely on logical axioms that again rely on utility templates. An example of utility template is something that represents here something called a typed list relation. And those again rely on base templates such as the OTTR. These different layers, they can then match or be built by people with different competence. So the system templates would be handled by people who know the databases, while the domain templates would be built by subject matter experts. What we want is that people create a template library that goes with their vocabulary or ontology, because the modeling patterns then represents the typical use of that vocabulary. So it's much easier, we think, to, for instance, use the or understand the pizza ontology by looking at the patterns than just by looking at the ontology as a whole. So this has brought me to the summing up. So why should one use OTTR? OTTR is a language for representing and therefore also sharing and using modeling patterns. And you should be convinced by looking at cases from software engineering that patterns is the way to go. We need better abstractions over the low-level languages of RDF and OWL. By using a pattern mechanism like OTTR, we can have more consistent and correct modeling. So we have the signatures that ensure consistent modeling, and we have things like type checking to ensure that we instantiate templates correctly and also create templates correctly. Once you have your template library, creating ontologies become more efficient, because you have the power of these abstractions readily available, and with efficient tools like the spreadsheet tool we saw and the mapping language, it's easy to create a large number of instantiations of those instances. This also represents arguably, and I emphasize arguably, so some people will not like this, I guess. But the patterns and the tools that come with them make it easier to also create templates. Sorry, ontologies and knowledge bases. By using OTTR, you can also organize your patterns in a library. So our templates can represent patterns in a compositional way, which allows for this graph structure of templates. And it makes it easier to organize the templates. And this is my last point. So if you want more information, please visit the site. I demonstrated parts of the primer, but there are also more interactive examples. There are some video tutorials and also interactive tutorials and papers. And with that, I say thank you.
Well, thank you very much, Martin. We have some time for questions and comments, and I see that James already has his hand up. So why don't we turn it over to James?
I was clapping first, but I also had my hand up. Thanks very much, Martin, for presenting, and thank you for struggling through your cold.
Yeah, I hope it came through okay.
Yeah, it certainly did. So we haven't met before, I guess, but yeah, I work very much in the OBO community, and I designed and did a lot of the development on Robot, which is an OWL API automation tool. And in OBO, we have two approaches to templating, and neither of them are as like complete or carefully designed as OTTR is. One of them is called DOS-DP templates for dead simple ontology patterns, and it's like a Python library, and it emphasizes, like, one of its strengths is string templating, concatenation, and kind of variable substitution inside of strings. And then Robot is the Robot templates I designed, and they are very much focused on OWL Manchester syntax string substitutions into Manchester expressions. So my specific questions were just about clarification. So does OTTR allow you to kind of substitute inside of a string, like an RDFS label, to concatenate something? And does OTTR allow you any way to put like an expression, like a class expression, into a slot? Yep, that's it.
So the first question is, I translate that to, can OTTR do term manipulation, or run functions over the arguments? And the sad answer is no. And it's of course a big wish to have something like that. Our answer to this is we have created a functional language that can manipulate terms, and it uses the same typing system as OTTR has. It's not available yet. It was recently published as a master thesis, so we haven't included it yet. With the name of that language is called FROG, Functions for Ontologies, and the idea with FROG is that you can create functions, and in a similar way as I demonstrated for the template library, you can publish the functions in a library and make them available in a similar manner. So in all the places in a template where you see a variable or a term, you could also there have a call to a function. The details of this is yet to be detailed. Sorry. But it should work as a the functional language is inspired by Scheme. The second question was if you can include a class expression in a template, and the way you would do that is by I think you could say that. So this would be a way, I could claim that I'm doing it here, I think. So here I'm inserting a class expression which is a class defined as a union of classes. So I do that by, here I'm using blank nodes, but it didn't have to be a blank node, but here I have an expression that creates this class expression, and it assigns it, if you will, to the blank node B1, and then it uses the blank node as an argument in a different template. I'm not sure if that is an accurate. Okay, yeah.
The thought is, so instead of saying whatever, I don't know how to do it for the pizza example. Instead of saying like A is subclass of B, and my slot I'm filling in is with a class B, a named class. Instead of that, I want a class expression like whatever C part of D, and so I want to put that into my slot. So if I have a blank node for specifying that class expression, then I could put it into one of these slots. That's okay, I guess. And then,
yeah, so no, sorry.
But the context I have is usually filling in templates like Excel files, like you started with, or CSVs. So right now I don't see how to do that, like an expression like whatever C part of D, and put it into a slot.
Yeah, no, you wouldn't either. You wouldn't do that in. So these variables, they wouldn't take a whole class expression. They can only take a single value, and also you cannot send in a template instance, for instance. So you can send in an OWL class, but I mean the definition of that OWL class needs to be somewhere else. So we don't take. I guess one answer would be that the type of the parameter would be a list of axioms or something like that, and that I think would go a bit against how Otter is designed.
Cool. Thank you for answering those questions. Looks like Jim has a question.
Yep. You're muted, Jim.
Oh, thanks. Yeah, thanks for your presentation, Martin. Yeah, I was actually going to ask kind of the same question as James, just because I'm the developer of the DOSDP software that like the other pattern system that we use, and so yeah, I was going to ask about the string substitution as well. But I really like Otter. It's way more general than DOSDP, and so it is very nicely designed. And so yeah, I'm looking forward to maybe trying out that to be able to define functions. The way we substitute strings now, you know, they actually query the input ontology, like to find labels for mentioned terms. Like here, if you're passing in like the toppings, we might like look up the label of each of those and then use that to generate maybe some property value for the pizza here. So that was more just a comment because James already asked the question, but I'm curious, in this, every time you instantiate the name pizza pattern, is the B1 blank node, is that a fresh blank node every time? So that the B1 doesn't mean anything necessarily?
Yes. So
Okay.
And that's a good question. It's so by specification. So
Okay.
we have specified that if you use a blank node in the definition of a template, then it's minted fresh every time it's instantiated.
Thanks.
I would like to extend my answer to this string concatenation question. The way we do it now is, of course, because we have the same issues as or wishes as you expressed, is that we put the string concatenation in the query. So where is it? Yes. So of course, Sparkle and SQL query languages can do string concatenation. So the way I would do it now is that I would have to use this query language in a sense to some data preparation steps before I can instantiate my templates. You can, of course, also do string concatenation in Excel. So I could create a temporary or auxiliary column, or what to call it, and then I could say that this is computed by the value in this or something like that, and that would also work. So the machine would pick up this computed value. That ends my comment. I see Ravi has his hand up.
Yes, but before we get to Ravi, Michelle McGee asked, can you say more about the Otter triple?
Yes, so the Otter triple, so I use that here. The Otter triple is a specific type of template which we call a base template. And a base template is a template which has no definition in the same sense as we see here. So here the pizza template is defined by these templates, while the triple template is a base template, which means it doesn't have a body, but its expansion is specified in software. Or, I mean, it should ideally, and its expansion is defined in writing in a specification. And the Otter triple means that it represents an RDF triple. This reminds me of the fact that we can also have other base templates, depending if we specify them and also implement them. So we could have a base template for, I don't know, making sounds or all kinds of weird things. I mean, so I could have a template which is called play a sound, and depending on the input, plays the sound which accurately represents the input. A more reasonable example is to have base templates that represents OWL axioms and would then represent them as OWL axioms using the OWL API. So I could then create a template language that always expands into instances of the OWL API. Was that
Ravi?
yes.
Thank you, Gary and James. I have a good feeling, very good feeling about today. What you said is something I think beyond what we've been generally hearing. So it's a path-breaking area, it looks like. But let me try to understand you all. First, let us think about OTTR. What is it that is its power? Is it the number and variety of classes? Is it the patterns? Or is it the ability to generate functions that give you outputs like vocabulary?
Should I answer first, or does anyone else want to answer?
Yes. And thank you, Jim and Chris, for doing some interim replies to my questions on the chat. Yes, Martin.
So it's a very good question, and it's one that I've asked myself a few times, because I mean the OTTR language is a very simple macro language, and you can do much more powerful things with programming languages, and people have already created those. I fail to remember the name now. So why OTTR? I think because this is designed specifically to be simple and fits with the expected expressivity for data modeling or knowledge representation. I think that's my best answer. Okay. I would be happy to hear.
I know you have given us the whole URL there, OTTR.xyz, and I went there for a brief time while you were talking, and it's very enlightening. There is a lot of stuff there which we need to absorb. So I am very curious about the vocabulary extraction part. Can you kindly say a couple of words or lines?
So if I understand the question correctly, OTTR is not capable of extracting patterns from an ontology. Is that what the question is?
No. The question is that somewhere I saw a statement that you could extract vocabulary out of these patterns or classes or solutions that you are working on. So how do you generate vocabularies? Because that's a big part of solving the semantic problem.
Okay, so is the question how you can use OTTR to create an ontology?
More than that, a part of ontology which deals with terms and vocabularies. Vocabulary, maybe my V is pronounced poorly. Vocabulary.
No, I think I understand the question, but I'm not sure if I understand what it entails.
Okay,
So
do you have anything in what you presented today that would help us extract vocabularies?
no, you cannot extract things. You
Okay,
can only
so I misunderstood something.
So I have maybe a related question about the top-down modeling, which sort of gets at that. Is it the case that you find that you can actually have domain people who know the vocabularies actually use this to create, and then the database people actually can use it for their particular purposes? So down the from the top down to the bottom, is that the case that you don't need ontology specialists to do some of the modeling?
Well, this is a bit of hand waving, I would say. So the idea is that these layers would work similarly as programming APIs would. So I can, in the same way, when I do programming, I can use an API without understanding how it functions really, or I don't need to look under the hood.
Yes.
This is just the same idea applied to modeling with patterns. So I mean the domain people of course need to understand the patterns that they use in order to create their domain templates, and how can they do that without looking into the details. They will do that in the same way as I do when I understand APIs, and that's by looking at examples and reading the documentation. If I am curious enough, I can look into the source code of the API, but I rarely do that. It's
Okay,
usually
all
enough
right.
for me to read the documentation.
One quick one, Gary, is for Martin, the templates and patterns and these APIs. How do these help with metadata, and what is the metadata about? Is it about pattern, template, or the API?
So there are different types of, or I can understand the term metadata in different ways. There is a special type of instance which we call annotation instance. So I can, by using instances which are attached to a template, I can create metadata about the template. That would be who created the template and so on, but also documentation in the form of examples or an explanation. And I think I can demonstrate how it looks like. So here, let me zoom in. So here is the signature of my template, and here is the body like we've seen in the slides. Now
Yes.
I can also attach an instance. So here I'm using an instance of a template which is called version, and I give my template a version. So this template named pizza is given the version 022, and here I'm not sure what these arguments are, but I also give it a status which is draft. We have created different annotation templates, to call them that, or metadata templates, which are these ones. So you can specify some provenance information, you can define, or not define, but explain the parameters, explain the signature, and mark a template as deprecated, and change notes, and so on.
Thank you. And how do you handle NoSQL or non-RDBMS databases? You do handle Excel spreadsheets well, but I was just generally asking about NoSQL.
So in general, we could handle any query language which where the answer to the query is a table. What we have implemented is support for SQL and Sparkle. Our use cases have also asked for support to convert JSON tables. No, sorry, JSON data, and also XML. The problem there is that the answer to queries over this kinds of data is often hierarchical, and it's more difficult to create instances from a tree than instances from a table.
Yes.
So
yes.
it depends. It depends on the query language over the databases that you mentioned.
Thank you. Thank you so much.
Yes, and we're well over time, so I want to thank Martin and everybody for a very exciting session, and I'm sure there's going to be some follow-ups, so your site is going to get hit, I'm sure, a few times and be useful. I just want to remind people that next week we don't have a formal presentation. We've concluded with Martin on a good note here, but we will start to do our synthesis. I did a synthesis of the first couple in introducing the panel last time. I'll try to do a little bit of a synthesis again as input to the synthesis session, and people are invited to come and to provide their thoughts about what comes together, what issues remain. And the synthesis session of next week will be followed by session on our formal communique, which, as you might know, is drafted for a publication in Applied Ontology, and we'll have more details on that as we get closer to that. So with that, I want to thank everybody for coming, especially Martin, and look forward to people coming next week and starting on putting things together so that it can be useful for the community. And I see James is James applauding, or does he have a hand up here?
Just clapping, just clapping. Thank you, Martin.
Clapping, okay. We all deserve some applause. Thank you again, Martin. Okay.